So this chapter is called Analyzing Starlight. The vocabulary for this chapter is apparent brightness or just brightness, brown dwarf, color index, giant, luminosity, magnitude, proper motion, radial velocity, space velocity, spectral class. So we'll get to those as we go. Everything we know about stars, their size, mass, temperature, age, velocity, distance from us, composition, whether they're a single star or multiple star system, and so on, is determined by analyzing starlight, that is to say, light from them. All we can really do is aim something at a star, gather the light from it, and examine it. And it's amazing how much we can learn from that. All of the things that I just listed and more. We can't travel to them. We can't go get something from them. All we can do is look at that light. So we're going to start with talking about brightness. We've talked about this a little bit before. There's a difference between the thing we call luminosity and the thing we call brightness. And luminosity is kind of the wattage you have on a light bulb. So you might have a 100-watt light bulb. It's just a property of the star, the way it's a property of the light bulb. The luminosity doesn't change if you get closer to a star or farther. It's just the total wattage of that star. But the brightness, or apparent brightness, does. As you get farther from a star, just like when you get farther from a light bulb, it gets dimmer. So this equation right here, B equals L over 4 pi r squared, relates the B brightness to the L luminosity and the R, the distance it is away. And so if you just remember a little bit of your math, and I won't ask you to do any real math, but there are only three unknowns in this equation, B, L, and R. 4 and pi, we already know what they are. It's the same thing with the 2. And so if you remember your algebra, if you only have one unknown, you can determine it. So if you know the luminosity of a star, its wattage, and you know its brightness, which you can just measure by looking at it, you can determine how far away it is. This is done a lot, and this little technique allows us to determine how far away stars are. So to understand how astronomers specify brightness or apparent brightness, those two mean the same thing, really. They use magnitudes. This was started by the Greek astronomer Hipparchus, who developed a brightness scale for stars. Humans can only see down to a certain dimness of stars. And the brightest stars in the sky, Hipparchus said are magnitude 1 stars, and the dimmest stars he called magnitude 6 stars. And so they're separated by 5 magnitudes. Astronomers have since sort of scienced Hipparchus's technique a little bit, but it's more or less remained the same. And it turns out that a star of magnitude 2 is about 2.5 times dimmer than a star of magnitude 1. Similarly, a star of magnitude 3 is about 2.5 times dimmer than a star of magnitude 2, which makes it 2.5 times 2.5, or 6.25 times dimmer than a star of magnitude 1. If you do that 5 times and compare a magnitude 6 star to a magnitude 1 star, those differ by about 100 times. So a magnitude 1 star is about 100 times brighter than a magnitude 6 star, or it would take 100 magnitude 6 stars to be as bright as one magnitude 1 star. So what we've done since Hipparchus also is to extend this range. And so we let the magnitudes in the brighter range, which takes them into negative numbers, go from 1 to 0 to -1, -2, -3, and so on. And in the dimmer range, 6, 7, 8, 9, 10, 11, 12, and so on. And so if we, let me just pull up a couple of pictures here. Uh-oh. There we go. I think they're up here. Okay. And so here's a range of brightnesses for a whole bunch of different objects. And if you can see, we're back on the magnitude scale here. So here's 1, and over here is 6, the faintest object that can be seen by the naked eye. Betelgeuse is one of the brighter stars. Sirius is actually a minus 1.5 or 2 star or something like that. But Hipparchus probably would have cataloged it as a 1, I'm not sure. So this is our range of sort of stars that you can see with the naked eye. It ends about here. But if you've got a pair of binoculars, you can see all the way down to a magnitude 10. If you've got a 1 meter diameter telescope, our telescope at the observatory, which some of you got to see, is about half a meter. And so it's probably like a 12 or a 13 magnitude maybe star that you can see with it. A 1 meter telescope is a research grade Sirius telescope. A 4 meter telescope, you can see at 26 magnitude. The Hale telescope is in, I'm not sure where it is. The Hubble's in space, and it and the Keck can see 30 magnitude. Remember, it's a factor of 100 for each 5. So if you look at 0, it's 100, 10,000, a million, 100 million, 10 billion, a trillion times dimmer. So the Hubble can see something that's a trillion times dimmer than the brightest stars we see. And so that's why these telescopes are useful, because we're looking at very, very, very dim objects. Notice as we go in the brighter range to the left in this graph, Sirius is the brightest star you can see from Earth, right? It won't be forever. That'll change eventually, because we're all moving away from each other or towards each other, and some are moving faster than others. Jupiter and Mars at their brightest are about 2.5 or 3, minus 2.5 or 3. Venus is the brightest object besides the sun and the moon you can see from Earth when it's bright. The full moon is like minus 12.5, and the sun is like minus 26 or something like that. And so this gives you kind of a scale, all of these magnitudes here. I think that was all I had to say about that. Let me just pull back down here. Yeah, okay. So you should be able to see that, a magnitude minus 4 is 100 times brighter than a magnitude 1, because they differ by 5. Okay. So now let's talk about the colors of stars. You just saw that picture a second ago. Let me see if I can scroll back up to it real fast. So here it is. When you look at, this is just taken of a collection of stars. And when you look at it, you see all different colors of stars in there, right? And so let's scroll back down here. And we can look at star color and correlate that with a lot of other information about the star, but specifically the temperature. Blue stars are about 25,000 Kelvin. And remember, you can kind of double that to get the temperature in Fahrenheit if you want to think in those numbers, but I'm not sure it helps any. White stars are about 10,000 Kelvin. Yellow stars, sun-like stars, are about 6,000 Kelvin. Again, this is at the photosphere on these guys. Orange stars are cooler yet, and red stars are the coolest. And by the way, this doesn't really correlate with their brightness, because how big they are matters in brightness. And so Betelgeuse is one of the brightest stars in the sky, but it's also one of the coolest. It just happens to be enormous. A giant bonfire that isn't very hot is brighter than a small bonfire, a small fire that's really, really hot. So astronomers like to look at the colors or the light that stars are giving off and do things with it. And another approach they use is what's called color indices. And so instead of just using one single color like we've done here, we'll use a range of colors. So we'll look at a star in the ultraviolet range, and then we'll look at it in the blue range, and then we'll look at the yellow range, which we call V for visual, because yellow is in the middle of the visible range. And so this would be the UBV scale, and they give a number for each one of those. and that categorizes your star according to how it emits in ultraviolet, blue, and yellow in those ranges. More sophisticated still is, what did I do there? There we go. Is to just take the spectrum of each of these stars. So we looked at atomic spectra, emission and absorption spectra, way back in chapter, 5 or 6 or something like that. And we showed that if you're looking through the atmosphere of a star, you will see dark lines on the front of a continuous spectrum. And so what we've done here, or what the authors have done here, is taken a whole bunch of spectra of different stars. The label on the left is the type of star it is, called its spectral class. And then to the right of that is what its absorption spectrum looks like. Remember, the dark lines indicate the excitation levels of the gas that is surrounding the star, right? And so you can kind of see these kind of vary continuously from bottom to top or top to bottom. They vary smoothly. And you can tell a little bit about what's going on there. First of all, we've got the letters out in front. They go O, B, A, F, G, K, M. In addition to that, we have some numbers. Each one gets a 0 through 9. And so the top of this chart is the hottest stars. So the O stars are the hottest. And the bottom of the stars are the M stars, and they're the coolest. And you can see that a little bit because the M stars have more red than blue, and the O stars have more blue than red, right, as you move up. A lot of interesting things are happening here. Let's look at this A1 star. This A1 star, you can see kind of a dark line here, and a dark line here, and a dark line here, and a dark line here. That's the set of visible hydrogen lines that we looked at way back when we were looking at atomic spectra. Those are the hydrogen lines. It's excitations out of the first excited level, the n equals 2 level of the hydrogen atom. And what you'll notice as you get to hotter stars, you see less and less of that. And as if you get to cooler stars, and you get less and less of that. And the reason is that line is dark because A1 stars have lots of excited n equals 2 hydrogen atoms in there. The O stars are so hot that the electron in the excited state of hydrogen has enough energy to just leave completely often. And so the atom is no longer able to absorb and re-emit these particular lines of light. Similarly, cooler stars, the hydrogen atom is in the n equals 1 level, not the n equals 2, and so it also can't produce these, it can't handle these excitations. And so if you get much hotter or much cooler, than an A1 star, those hydrogen lines are less visible. All these other lines are different elements that are involved in different excitations that, depending on what the temperature of the star is, are darker or lighter, just depending on how it goes. You can notice that the M5 has a whole array of dark lines. That's because it's got the lowest energy, and so it even has molecules together. These hot stars up here don't have any molecules, and so they can't handle any of those excitations. And so this is what we see for the spectra of these stars. And so this is how we catalog them. We take stars and we take an absorption spectrum of them, and then that tells us lots of things about the star. We'll talk about more as we go. So the picture above, the Nebula spectrum is 13 different stars, from cooler at the bottom to hotter at the top. From hottest to coolest, from top to bottom, they go O, B, A, F, G, K, M, and each letter is designated with 0 to 9, with a 0 to 9, with a 9 at the cooler end. The sun is a G2 star, and so G2 is the sun's spectral class. So you can remember the O, B, A, F, G, K, M as O, be a fine girl or guy, kiss me, O, B, A, F, G, K, M. And so if you can remember that, that's an easy way. The spectrum of a star also indicates its temperature and its color, and so in many ways, those are redundant. The spectrum of a star gives you just more detail that you can learn, but the temperature tells you a lot of that, and so does the color of the star. I'll talk more about other things we can get from the spectrum of the star in just a little bit. So this section says, explain the difference between a star and a brown dwarf. So here's the thing. If you want to be a star, at some point in your life, you have to be providing 100% of your energy from fusing hydrogen into helium. That fusing hydrogen is what makes you a star. And if you're not doing that, you don't get to be a star. And so brown dwarfs are objects that are not quite hot enough in their core to be fusing hydrogen into helium. In order to fuse hydrogen into helium, you need to be about at least 7% of the mass of the sun. If you're below that, you're a brown dwarf. So a brown dwarf is an object that has a mass from about 1% of the mass of the sun up to about 7.5% of the mass of the sun. A brown dwarf isn't fusing hydrogen, but it's warm for a long time due to the Kelvin-Helmholtz contraction that we talked about several chapters ago when we were talking about the gas giants. When those objects contract, they generate heat. And they contract fairly slowly, and so they can generate heat for very long periods of time. And so brown dwarfs are giving off heat due to Kelvin-Helmholtz contraction, primarily, sometimes other things. We have spectral type letters. O, B, A, F, G, K, M extends to L, T, and Y if you're going to add successively cooler brown dwarfs. So let me hang on a second here. Whoa. I think I need to go up. I lost my place. All right. So the range of masses of brown dwarfs is from about 13 to 80 times the mass of Jupiter. Interestingly, they're all about the same size. So despite having different masses, these brown dwarfs are all the same size. Let me see if I can give you an example of that. Here, notice this is the sun up here. Oops. Let me try that again. Right, there's the sun up there. And here is an M1 star, right? That's the hottest end of the M scale. And here's an M8 star, right? And notice as we get to LT and Y and then all the way down to Jupiter, which isn't a brown dwarf, it's just a planet, all these guys are about the same size. And so their masses are different. It's just that as they gain mass, gravity gets stronger, it makes them more compact. And they have to gain a lot of mass before they actually start getting bigger again. And so all brown dwarfs have different masses, but the same size, roughly. Off the page a little bit. There we go. Okay, so here's so if we take the stellar spectrum like we were talking about earlier, so if we look at these guys, right? If we look at those spectra, we can learn some things about the stars. We can use the stellar spectrum to measure radius, composition, motion. Just the fact that we can see those dark lines gives us some information about what elements are there: hydrogen, helium. For the cooler ones, you can find molecules and things like that. Here's another picture off the PowerPoint, but here are the spectral classes across the bottom here, right? And this tells you kind of what's going on. We have singly ionized helium, so the lines you see on an O-type star will have singly ionized helium lines. None of these other stars have ionized helium at all, so you won't see any of those lines on these guys. Similarly, you can see excitations out of the neutral helium for stars in this range, out of hydrogen for stars in this range, out of ionized metals for stars in this range, right? You can look. And so all of these, the dark lines, how they correlate with the different elements in this chart, allow you to figure out what the spectral class of your star is. So here's some things we can do to learn more about the stars. For example, two stars with the same spectral class will have the same spectrum. That's what that spectral class means. They'll have absorption lines in all the same places. However, if one of them is a small, compact star, like a white dwarf, which we'll talk about in the future, it'll have a higher pressure atmosphere compared to a large star. The high pressure in the small star spectrum will give rise to thicker absorption lines than are seen on a large star. So the spectrum can be used to indicate the size of the star. So let me see if I can give you a picture of that. Let's come back up here. So here is a blue giant, right? A giant star is a star that's very large. And here's a white dwarf, which is, even though it has the mass of a star, it's very compact. The sun will be a white dwarf at the end of its life. Notice we can see that that the dark lines correlate. They're all in the same places, right? But the compact star has thicker ones, and the giant star has thinner ones, and that's because the high pressure here means molecules that are emitting these lines on the compact star are under high pressure, and so sometimes they have a very high velocity toward or away from the viewer, and that broadens these lines a little bit. And so even though two stars have the same spectrum, you can sometimes tell a little bit about them, like, for example, their size, based on the thickness of the lines, of the absorption lines. Eeh. I don't know what I did there. How if I do that? So also, we can use the Doppler effect to measure the rotation of a star. Absorption lines in a star spectrum will be red-shifted as the star is moving away, or they'll be blue-shifted if the star is approaching. And so we can tell if the star is moving toward or away from us. We can also tell if the star is rotating. And so let me, using the Doppler effect, let me go back and, boy, I'm having a little trouble with that right now, aren't I? Here we go. All right. So let's look at these guys. Right. So this is the spectrum of three identical stars, right? The top one is redshifted, that is to say the stationary one, the top one is shifted to the red, and so it's going away from us. The stationary one is in its normal position for these lines, and the bottom one is shifted to the left, so it's approaching us. The bottom one is blue shifted, so it's approaching us. The top one is red shifted, so it's moving away, and the middle one is stationary. And how far the shift is tells us what the speed is that it's approaching or receding. I think I was going to do a rotating star there also, maybe. Okay, I'm going to skip this and come back to that, I promise. So here's what happens with a rotating star. Almost the same thing as with a large and a compact star. So here's a star that's not rotating, and you can see light from the left side and the middle and the right side all has the same wavelength. However, if the star is rotating, right, then the star from the side that's approaching us is blue shifted, and the light from the side that's receding from us is red shifted. And so if we're looking at the spectral line is broadened. And so once again, the width of the spectral line gives us a clue about what's going on with the star, if it's rotating or if it's big or something like that. And you might say, well, how would you straighten that up with the big star and the small star? And it turns out the way these are broadened is subtly different, whether you have a compact star versus a large star, or whether you have a rotating star. And so astronomers can tease out the details of that and figure out if one star is bigger and one star is smaller, or one star is rotating, one star is not, or some combination of those two things. I've completely lost there it is. Okay. So in addition to rotation and size and whether or not it's moving towards or away, by the way, the towards or away is measuring the radial velocity. And so we'll come back to that in a second. So we can also measure the proper motion of a star, and this is a little more straightforward, at least conceptually. So if we look at a star, let me go back to this one again. Here's, for example, a famous star called Barnard's star. There it is. Notice the background in each of these pictures is the same, but the star with the date next to it is Barnard's star. It's what's moving. Everything else is in the same spot. So Barnard's star isn't moving towards or away. It's not moving radially. It's moving perpendicular to that. We would call that transverse motion. But this is called proper motion in the astronomy world. And we can just measure the rate at which the angle it makes with something else or with our horizon changes with respect to time. And so it's called an angular velocity. But it's just moving across our sky rather than towards or away from us. And so we can look at what stars do, how they're moving, and see what they would look like in the past and what they look like in the future. Here's, for example, the stars of the Big Dipper. The center picture is how they look today. Oops. The top picture is how they looked 50,000 years ago, and the bottom picture is how they'll look 50,000 years from now. And so the proper motion is what tells us what positions does a star they'll look like in the past or the future. So here's a picture. Here's the star, the radial velocity. That's the one we get from the Doppler shift. Dang it. Right. That's this picture. The radial velocity is this velocity this way. That's what we get with the Doppler shift. The transverse velocity is what we get from the proper motion. And if we put those together, we get the space velocity. And that's how fast the star is moving relative to the sun, relative to us, if you want to say it that way. And so an arcsecond is a 3600th of a degree. Remember, a degree is about a fingertip at arm's length, and so divide that by 3,600. And that's what you'll see. I mean, that's the rate at which they measure these motions. They're extremely small. Even stars that are moving fairly quickly compared to other stars are moving really slowly on human life scales. So while the Doppler shift will tell the radial motion of a star, it won't determine the star's lateral or proper motion. For this, the star must be imaged over extended periods of time, just like we showed you the pictures, so we can tell how it's doing that. If we combine the proper motion and the radial motion to determine the star's velocity, it's actually speed relative as it moves through space relative to the sun. We call that the star's space velocity.